and then we'll jump in.
We're live. We're good to go.
Hello, everyone. Welcome to the conversation. We're talking about life on planets. My name is Jeff Kuhn. Call me Dr. Jeff. I'm joined with co-hosts Dr. Svetlana Berdugina. Say hi, Svetlana.
Hi, call me Dr. Svetlana too.
Okay, and Kevin, surfer legend Lewis is here also. Kevin, say hi.
Hello, everybody. I'm Kevin Lewis.
Okay, so Svetlana, what are we talking about today?
Oh my God, we're talking about this Proxima Centauri life, and I believe it's there. We just have to find it. And once we have bigger telescopes, we'll find it. Let's talk about it.
Okay, Kevin, you said you had a bunch of questions.
Perfect. I do. I'm pulling those up right now. So just give me 1 second.
So I should remind folks that our focus here is on understanding implications for life on the universe, and our discussion walks around the theme, are we special, and why not being special is a good thing.
Right. All right. So the first question that we wanted to talk about today. So how confident are we that Proxima B is actually a rocky Earth-like planet versus a planet that's mostly made up of gas? So can you talk a little bit about how we know for sure that it's a rocky Earth-like planet? Maybe Svetlana, if you want to talk about that.
Sure. We know that the minimum mass is 1.3 Earth masses, and this is assuming that minimum mass you get when the orbit is just edge on. We know it's not edge on, it's inclined. And so that if you incline the orbit more, you get the bigger mass. But, you know, if you do like approximate, say, on average, this planetary orbit inclines 60% to the line of sight, or even 45%, what you get is still mass about 1.5, 1.7 Earth masses, and that definitely not gas giant. This is definitely something solid. So, of course,
wait a minute. How can you say for sure, without a shadow of a doubt, that it can't be a gas giant?
That's what I'm getting at.
I just wanted to say that if your orbit incline much more, you have to divide by a smaller number. So it works this way, that if you incline orbit from this position to the line of sight to this position line of sight, you have to divide by smaller and smaller number, and dividing 1.3 by small number, in the end, you can get very big number. It can be very big if it's like that, yes. But then we don't see radial velocity changes. If it is like this, we don't see radial velocity changes at all. And we do see some, so it has to be inclined.
Yeah, but the argument, right, is still whether we're completely certain that it's a rocky planet. And I think, isn't that based on the fact that it's so close to the star that the radiation environment is likely not to have left much of a gas giant behind?
Well,
I haven't
possible
seen a really
too.
good
Yeah, it's indeed. I mean, it depends on the initial mass. So some calculations show that if you have a Jupiter mass planet, it takes pretty long to evaporate it, even if it's very close. And we see hot Jupiters at such orbits; they are not evaporated.
Yeah, but the truth is, we don't have a measure of the density yet. And
well, we do for hot Jupiters. They are low densities and they're on the same orbits.
We're not talking about that. We're talking about here around Prox B. Around Prox B, we don't have any measure of the density of this. We have a measure of the mass.
Yes, definitely not.
So hang on. Let me get this right. So the argument is that there's probably so much radiation around the star that if it was an actual gas giant like Jupiter, it would have stripped away all of the gas. So it has to be a rocky planet because of the radiation from the star. Because of how close it is.
That's kind of a weak argument, isn't it? My sense of this is that it's mostly theoretical arguments, that planet formation arguments that people were working from to argue that it has to be rocky, so close to the star. I think we should leave this as an open question that is, well, it's not completely open, but what is the probability that it actually has to be a rocky planet? That's a really good,
it's very high. So there's very low probability that it's a gas giant. Very low. There is non-zero, but it's low.
Okay, explain why that probability is very low.
Well, because we see I mean, it's low because to have that special, it's about, let's say this, there is how many transiting planets with respect to all planets we know? It's like a few percent. So I would say it's a few percent chance for the planets to be on the orbit like this, equal to the few percent of the chances for the orbit to be like this. This is special orientation of the orbit, one of the two. This is the same few percent. So I would say it's the same probability to see transiting planets and to see planets in the orbit which is completely in the plane of the sky.
What's the lowest mass gas giant we know about?
The lowest
mass gas giant. Yeah.
Well, I mean, if you look at Neptune sizes, this is like half or fraction of a Jupiter size mass. Yeah.
Yeah.
So. But again, it's like there is a continuum. It's not that we know there is like these super Earths, yeah, and we don't know actually how to. There's a continuum of masses, continuum of densities between very small and large planets. So there is no like abrupt change from gas giants to rocky planets. We have no Neptune size, Saturn size, super Earths.
Yeah. Okay. All right. So let's go with that. It's most likely a rocky planet, but you know, your question, Kevin, we can't rule out that possibility.
Yeah. Well, we talk about speculations today, so we speculate that there is a few percent chance.
But the truth is, giant. the truth is that the radiation environment is really ugly, right? So here's
it's terrible there.
So this is a star that has. I checked this the other day. This is a star that has only 2% of the surface area of the sun, but it creates flares which are larger than the sun.
Yes.
And so it seems to have this sort of continuous flaring environment, which incidentally is part of the reason why it's probably going to be hard to know whether or not it's actually a transiting planet, because the brightness of Proxima Centauri is always varying. It's the star has these we call them, in the case of the sun, we call them white light flares, where the brightness of the sun fluctuates. In the case of the sun, by a millionth, but in the case of Proxima Centauri, the brightness is going to fluctuate by due to flares by of order almost 1%, which means it's going to be really hard with that noise, that photometric noise, to know whether or not we have a transiting planet. It'll take many observations to establish that, I think. Would you agree, Dr. Svetlana?
Yes, I would agree. And I also want to emphasize why it happens. You know, well, like you say, why on the sun the flares are not so often, and on this little M dwarf it's so often. It's because these stars are totally turbulent. What we see on the sun is only upper layer of the sun is turbulent, and it's like boiling water, boiling gas there. Those red dwarfs like Proxima, they are completely turbulent, means that they're boiling completely through. And that particular environment, we believe from our models, that generate pretty strong magnetic fields, and which are kind of connecting, reconnecting, mixed by this turbulent motion. They brought together and they produce these reconnections, what we call, and strong flares. And these flares are much more frequent because field is much more entangled on this turbulent environment, more than on the sun, because that's something like on the sun we see on a small scale weaker fields, but if we magnify this several times in strength, in power, we will see a similar phenomenon on these M dwarfs, which are entangled fields reconnecting and reconnecting and rearranging themselves continuously, and that produce massive and frequent flares.
Yeah. Okay. So it's a. Go ahead.
I was going to say, I agree with you. That makes sense to me, and I'll have to track down this source, but I forgot what I was watching. But basically, what he said is, in the past, we thought that flares would be an issue, but new science has come out where it might not be that big of an issue, and they might not be that violent. Is there any theories out there stating that it might?
Yeah, no, I
might not be.
So the problem, well, it's not a problem, but the reason why I think we know quite a bit about Proxima Centauri is it's the nearest star of that. Well, it's the nearest star period, and so there's a lot of work that's been done to observe Proxima Centauri, for example, on X-rays, right? And we see X-ray flares more or less continuously. They're happening all the time, and then we see these photometric fluctuations also. So it is kind of the perfect star to study flares on of the size that it is,
right.
And we know a lot, and I think its activity is much more so than the sun. The X-ray environment and the high energy particles and everything that goes with that is going to mean life is different. The other.
Well, I disagree here. So if the planet has a magnetic field, then it is a protective shield from the activity. So the same for the Earth. Earth has magnetic field, and the sun is active. We do have flares, okay, not so strong, but still we do. And the magnetic field really shield us from these particles coming from the sun. They are just going by magnetic lines around the Earth, and they hit the poles, as we know. So the poles are hit, and we see polar lights. And this consequence of this interaction of the solar activity with the magnetic field of planet. And that's exactly why we need magnetic fields to protect the atmosphere evaporation and so on and so on. And
how much
so
stronger?
the life may not be different if the planet has magnetic field.
How much stronger would the magnetic field have to be?
Oh, it doesn't have to be too strong. Magnetic field of the Earth is pretty weak. It's fraction of a Gauss, so it's 10 times weaker than, even more, like maybe 20 times weaker than, say, average field of the sun. So it can be just very tiny, but it's enough to direct the particles around, not hitting directly the atmosphere, but going around and hitting the poles, okay, but also going into tail. Anyway.
Yeah, but the magnetic field isn't going to help us when it comes to ultraviolet radiation.
No, it doesn't. But for particles, it does.
And I think the other point here is that understanding what happens and how life evolves, if it evolved there, might benefit from a radiation environment. So the mutation rates and the things associated with some degree of radiation is probably something that accelerates the development, or certainly makes it different. I wouldn't argue that just because it's a higher radiation environment that we don't have life, or there isn't.
I would totally support it. Yes, definitely. I agree. Because, we talk like, okay, light is a source, stars are a source of energy for photosynthesis, and the optical light from the sun is used by the life on Earth, and ultraviolet cannot be used because DNA falls apart. But why should be sure that this is the case for all life in the universe? Maybe in some cases, UV and X-ray is a source, it's much higher energy, and it's source for energy for life of different structure, different from us. So we shouldn't dismiss that.
So since the announcement of Prox B, there have been several papers posted on it's kind of a new field, the calculation of atmosphere circulation and atmosphere properties in a planet that might be, we haven't talked about being tidally locked, but there's a decent probability that if it's an Earth-like planet and if it has an orbit like, well, it does have an orbit like we think, which is sort of well within the orbit of Mercury compared to the orbit with the sun, then it keeps the same face towards the sun, or it's in some other resonance where it orbits twice for every 3 rotation periods of the planet. So there's a possibility that maybe the tidal locking is what's called a resonance, and it doesn't always keep the same side facing the planet. But in this preprint on the archive, actually a lot of work is being done to show that if there's a fair amount of greenhouse gas, for example, if there's enough carbon dioxide, the water, the temperature of the planet, even on the dark side, if it's tidally locked, is sufficient to have liquid water. And if it were tidally locked and you were on the dark side, even the ultraviolet flux wouldn't necessarily be a horrible thing for you. So you could imagine a lot of scenarios where there are life zones on such a planet, and even with a fierce radiation.
Exactly. I mean, like on Earth, we also have parts which are not outside minimum habitability there, like in Sahara or like in Andes and so on. And we have places like that, and that's what we call also like extreme habitats, and other more suitable for life, others less suitable. So on the planet itself could be areas which are more habitable and less habitable. So we can talk about habitable zone in a sense like habitable longitudes, or because if it's locked, there could be longitudes where the climate is pretty moderate and nice. So there will be habitable longitudes and latitude as well, because if the axis of the planet is, for instance, vertical, perpendicular to the orbit, then poles will be much cooler, and it could be near the poles, habitable zones there, because then you would have not so much radiation on poles.
Yeah, and so exactly how that works is really dependent on, for example, how much CO2 is in the atmosphere or how thick the atmosphere is. And I probably I mean, it's interesting that there's a whole new field of planetary atmospheric dynamics that are going to develop for these systems that are tidally locked. Venus is a weird one too, right? Or in our system where planet rotation is
I mean,
so
this
slow.
is a complete generalization, but it just seems like, you know, like we have obviously life here on Earth, and there's seasons, there's distinct seasons. So the constant change is what's really important to have life. It just being static and not having change doesn't seem too conducive to have life, although I'm sure it can evolve in lots of different ways. But that constant change per year or frequently seems like it's beneficial to have life actually develop.
Oh no, I am not supporting that, because near the equator where the seasons don't exist, life just flourish. And near the poles where we have seasons, it's not, you know.
Well, I think
that's true.
I mean, there's the diversity that happens with the environment kind of leads to evolutionary pressure to change. I mean, this is an unexplored territory, and I think if we could make images of the planet around Proxima Centauri, we'd learn a lot. Which, by the way, should be the subject of another discussion: is what are our future prospects for actually getting a lot more information about the atmosphere of the planet. For example, well, let's talk about that another time. But
well, we can talk about it now a little bit. I don't know. But how will we actually? What is the next step to actually measure the atmosphere? How do we do that?
Well, so we at the Planets Foundation are keenly interested in how we build a telescope system that separates the light of the planet from the light of the star. So telescopes now, all of the world's largest telescopes that are in their construction phase, like the extremely large European telescope or the 30-meter telescope or the Giant Magellan telescope, they're constructed for collecting area. They're optimized to be able to get a lot of light from faint objects, and also to basically to be able to see big pieces of the sky at a single time. Um, go to our website and you'll learn a lot about how a telescope like ELF, thank you, Kevin, is designed to be able to see just exoplanet systems and to separate the light of the exoplanet from the star. No, those are not laser beams, but that image shows how the phase of all of the segment, the mirrors can be set in a clever optical system called an imaging interferometer.
Well, we
So,
already tested methods like that with, this is what Jeff tried to describe it, using polarization and combine it with coronography. And we already tested with smaller telescopes, and when you have a bigger ones, with all those properties available, we get our sensitivity higher and we can see smaller planets. Now we can see only big planets or giant planets. But later on, with bigger telescopes, we'll see. With this specialized bigger telescope like ELF and Colossus, we can see smaller planets too.
yeah.
And other than ELF and Colossus, are there any projects that can actually do this that are either currently built or on the horizon in the next couple of years that you know of?
Well, if you're very optimistic, the TMT could look at Proxima B and begin to separate the light. It depends on how.
No. If it's built in
successful.
Hawaii, you cannot see Proxima.
No, not in Hawaii. That's true.
Yeah.
It would have to be in the southern hemisphere. So
Yeah, so European.
So the GMT or the EELT
or GMT,
would be our best bet, but they have to achieve a level of scattered light that, for example, has never been achieved for the Keck telescope. Keck is a fantastic telescope for seeing big pieces of the sky. We say it has a wide field of view, but its scattered light is such that because it has many segmented mirrors, it'll be a lot of work to be able to get to the point of. We did a paper, Kevin, you've seen the results, where we took a planet and we let it rotate, and we did what's called rotational exoplanet imaging. And with a telescope like ELF, that one you just showed, we could make images of continents and oceans if Proxima B were Earth-like. I don't know. Do you have that image somewhere that we could bring that up?
Which one?
I think that what we can also talk is about atmospheric detection and detection life in the atmospheres. That's also possible. You know, you don't need to see really surface. If there is life on the surface, there will be some signature of it in the atmosphere. So when we detect atmospheres, we can already search for signs of life. On Earth, for instance, we have bacteria living in the atmosphere. There is aerosols, bioaerosols based on this bacteria. And imagine that if you have a planet which are like abundant on the surface, like we have here, by bacteria and some microorganisms which are capable of flying off the ground, then these bioaerosols, if they're abundant enough and we're sensitive enough, can be detected directly in the atmosphere. And that is also very exciting. That is a possibility which is not so far away, I believe. If such planets
Right, and the main
exist,
things that we're looking for are methane and oxygen. Those are the two.
Yeah, you can look at methane and oxygen, but I'm talking about real biological molecules, complex biology like protein and whatever it is, sugars or DNA or I mean complex molecules. Of course, we don't expect DNA there and very much, but amino acids and maybe protein as well. You know, amino acids are very common in space, so why not proteins? Look for kind of chains. Proteins are chains of amino acids, and that's something that we can look for.
Thoughts on that, Jeff?
So you're talking sort of about being able to do molecular spectroscopy.
Yes, or polarimetry, spectropolarimetry. Yeah, the same thing.
And that of course is there aren't very many photons that we get to use in that case, but maybe that works. I'm just talking about.
Yes, and it's like those absorption bands from proteins and kind of similar DNA, and so they're pretty broad absorption bands, and you don't need high resolution to detect them. This is advantage. These are complex molecules. They have many vibrational bands combined together, and they're broad in wavelength. So you need very low spectral resolution to detect them, which increase the chances of detecting.
Well, that also means that it's not very unique. If you're looking for very broad features,
sure,
there are lots of ways of making that, right?
Absolutely, and you have to combine things. You have to combine different biomarkers to make sure, to prove that this is life or not something else. Same with oxygen and methane. If you just detect them, it doesn't tell you that there is life. Okay, there is what you learn. There is oxygen and methane, no more. And then you start to speculate. Oh, if this possible, that possible, then it could be from life. You know?
Well, no, I think right. If we saw methane in the atmosphere of an exoplanet, that's a pretty good hint that methane doesn't last very long.
Sure, especially it's a hint, but it's not a proof.
No, yeah, in this business, there are hardly any proofs.
I mean, all our businesses are hard to prove. We're trying to kind of be reasonable and combine different facts together.
I mean, I would have thought that actually for Prox B, life in the atmosphere is going to be a hard sell because of the UV background from the star, and that.
You know, I think about Venus, for instance. Yeah, like some people speculate that unknown UV absorber in atmospheric clouds could be due to life. This is again a speculation. And we know there is life on Earth in a high UV environment, which like extremophiles who really like this high UV environment, and they do have absorption in the UV band. And so on Venus, there is some additional absorption nobody can explain yet, or there are different hypotheses, and one hypothesis is that this could be life. So there could be life which is adapted to even thriving in high UV environment, and it could be in the atmosphere, could be in clouds.
Yeah, I'd like to find life that we can communicate with, and communicating with sulfuric acid bacteria doesn't sound very exciting to me.
Well, speaking of that, and also speaking of indisputable proof, so you guys were part of a SETI hangout, I think like a couple years ago, and Frank Drake was on this hangout. And what he was talking about is he said that Freon was an indisputable proof that advanced life would be on that planet. So if we actually did find Freon, is it just like, that's it, that's life? What are you guys' thoughts on that?
Yeah, right.
Is there any way that if we detected Freon that it could be some other type of process other than, you know, some type of technology creating that?
So far, we don't know bacteria which produce Freon, so it must be intelligent life then.
Well, yeah, all right, but I mean, all of this is about what's in equilibrium, right? And so Freon, I think, is easily destroyed by ultraviolet radiation. And however we think about this planet, it's got to have a high UV flux in the atmosphere. So I don't know, if we see Freon, it means, and they got a lot of leaking refrigerators or something, but it sounds, I remember his comment, and I, you know, it seems like it's awful specific to a class of technology that might not exist or only exist for a part of time, but it doesn't last very long.
Yes, and the point here, I believe, is that it's not just particularly Freon we're looking for, but it's something like which is not produced by natural geological processes. So if we studying the geology and planetology in solar system help us understand which gases can be produced through natural processes and which cannot be. And so when we have that detection of gases which cannot be produced by natural processes, then it's a signature of the technology.
Right, but couldn't there be some really interesting, unique geological process that has some interesting condition that's actually making Freon somehow?
Wow.
I don't
I mean,
know.
I guess
Okay, all right. That's
Probably
that's
not.
all right.
Probably
that's
not.
All right.
So far, we don't know.
that's a good homework question.
Yes.
Let's write about that in your notes, Kevin. That's your homework.
All right.
Is there natural occurring chemistry that makes freon?
Well, or more generally, this chlorofluoride, whatever
Chloro,
they called, hydro
hydrochlorofluorocarbon.
carbofluoride, whatever chlorides.
Okay, we're gonna upset the chemists. We gotta be careful.
Yeah.
The
All
other
right.
reason, but let me just follow up with one other point that we hadn't mentioned here yet, which is that Prox B is maybe in a bound system with Alpha Centauri A and B, and it's in an orbit that's hundreds of thousands of years, and that orbit, we don't know what the closest distance
Right.
between those are, but that's a system that might change how volatiles, for example, get transported into the inner part of the stellar system that eventually made the Proxima B planet. And so there's this other possibility that Proxima B is very different than what we think of because of the fact that it's in this system that has multiple stars that are perturbing the gravity and would almost certainly have an influence in the early days, the first tens of millions of years when the planet was forming. So it will be very interesting to learn if Proxima B really is bound gravitationally to the other two stars. And I think that's still an open question. The truth is that they're moving in space. They have a high proper motion, and they're moving with roughly the same proper motion, although they do have a relative motion that's been measured between them. And I read one paper not too long ago that said, oh, the chance probability that they could be moving in the same direction as closely as they are is like 1 in a million. I'm not sure if that's been confirmed or not.
Well, I've seen a paper where they discuss actually of possible close encounters between these ABC components, and it's also possible that they were closer. I mean, what we see now, they're further away, but they could be closer before. And simulations show that it's, there's perturbation on the planets and on the planet formation. It depends on that, where there is a question, for instance, we didn't mention yet, whether this Proxima B was formed where it is observed now, or was formed somewhere else and then brought closer to the star through interactions and perturbations or migration, as we know possible. So this is also an open question, where and how this planet could be formed. And that actually influence the composition of that planet. If it's formed further away, it can have more volatiles before, and then it comes closer, it loses it, or how it could accumulate more volatiles necessary for life and atmosphere through interactions, perturbations, and so on. So that is something which is hard to answer when you have one measurement in space-time, like now,
Yeah, but I think the point we're making that we probably agree on is that the formation history for this planet was different than the Earth. And
yes.
So we shouldn't let our bias about what the Earth is like influence unduly what Prox B is really like.
And Jeff,
Yes,
you're saying that's mostly
absolutely.
because it's a multiple star system and that had a significant influence on the planet.
Yeah,
Right.
and just for the record, most of the stars in the sky are multiple star systems, so it's not unusual.
Sure.
It's part of the way the universe is put together. So
there you go.
Did we get through all of our questions?
I think so. I mean, we covered pretty much the majority of the questions. I think so.
All right. That was very interesting discussion.
Yeah, I'm liking these. We're they're each week they're significantly improving and getting better.
So
having fun.
Is Connor here this week? Is he?
Connor is. I'm not sure. I don't think he is.
Okay. All right. And next week, what did we have queued up?
That is to be determined. I don't know if we have an actual topic yet. Any ideas off the cuff, Svetlana, that you would like to talk about next week?
Well, we can talk about different kind of expectations for detection of the life, not necessarily just Proxima. I mean, we were focused so much on Proxima, and it's not excluded, but we can talk about biomarkers. What kind of, like you mentioned, and technomarkers. You mentioned freon. I mentioned some bacteria and photosynthesis. I think like, and oxygen and methane, Jeff mentioned. So maybe we can talk, just take this topic and say, what other detections will tell us that life is there on the planet? What's actually minimum?
Yeah.
What is minimum detection we need? Like, what's the, okay, you know, hints or whatever. But when we say, Eureka, there is life there.
Right. What does that look like? What do we need for that?
Yes.
Okay, so Kevin will fill out the notes, some of the things that came up that we referred to either fallaciously or correctly in our memories and in the literature. We'll put some notes down, I hope, and we'll spell hydrofluorocarbon correctly and solve the problem of whether or not there are geological processes that can make freon, for example. In the meantime, we want to thank all of those interested in the question of life on planets for joining us, and stay tuned next week when we continue the conversation. Thanks, Svetlana and Kevin.
Yeah, of course. Thank you guys.
Thank
Appreciate
you
it.
all. Nice to be here.
All right. See you next week.
Bye.
Bye-bye.